Welcome, everyone. I'm excited to kick off our presentation today. We're going to explore the fascinating topics of work and energy. This first slide simply introduces our subject with the title Work and Energy, and there's no subtitle here. Over the next few slides, we'll dive into how work is done, how energy is transferred, and why these concepts are so important in physics. So let's get started and enjoy the journey through these fundamental ideas. Let's take a closer look at the contents of this presentation. First, we have work, which is essentially the energy transfer that occurs when a force is applied over a distance. It's a fundamental concept because it helps us understand how energy is used in everyday activities. Next, we move on to energy itself, the capacity to do work. Understanding energy is crucial because it underpins all physical processes, from the simplest movements to complex industrial operations. Following that, we have the transformation of energy. This is about how energy changes from one form to another, like from chemical energy in fuel to mechanical energy in engines. Recognizing these transformations helps us optimize systems and improve efficiency. Then there's the commercial unit of power. Power measures how quickly work is done or energy is transferred, and having a standard unit allows us to compare different systems and performances accurately. Finally, we see the rate of doing work, which is essentially what we call power. It tells us how fast work is being done at any given moment. This ties everything together because understanding power helps us evaluate the performance of machines and processes in real time. Overall, these concepts are interconnected. Work, energy, their transformation, and the rate at which work is performed, all are vital for understanding how energy powers our world efficiently and effectively. Let's talk about what we mean by work in physics. Work is said to be done when a force acts on an object, and that object moves or is displaced in the same direction as the force. In simple terms, if you push something and it moves forward, you've done work. The amount of work done depends on two things: the size of the force you apply and how far the object moves in the direction of that force. Mathematically, we express this as work equals force multiplied by displacement, which we write as W equals F times S. Now, the unit we use to measure work is the joule, abbreviated as J to give you a sense of scale. If you apply a force of 1 Newton and it displaces an object by 1 meter, that's exactly 1 joule of work. It's a straightforward way to quantify how much energy is transferred during that process. Let's look at an example to make this clearer. Suppose you push an object with a force of 5 newtons and it moves 2 meters in the same direction as your push. The work done in this case would be 5 newtons times 2 meters, which equals 10 newton meters or 10 joules. So, in summary, whenever a force causes displacement in its own direction, work is done, and we can measure that work in joules. This concept is fundamental because it links force and movement directly to energy transfer. Let's talk about the different types of work that a force can do. The work done by a force can be either positive or negative, depending on the situation. When the force and the displacement of the object are in the same direction, the work done is positive. Conversely, if they are in opposite directions, the work is negative. And if there's no displacement at all, then the work done is 0. For example, imagine you're lifting an object straight up. The force you apply is upward, and the object moves upward as well. In this case, the work you do is positive because the force and displacement are aligned. But at the same time, gravity is pulling downward on that object. The work done by gravity in this situation is negative because the force of gravity and the displacement are in opposite directions. Let's look at a specific example. Suppose a porter lifts a 15-kilogram luggage from the ground and places it on his head, 1.5 meters above the ground. To calculate the work done, we use the formula W equals F times S, where F is the force and S is the displacement. The force here is the weight of the luggage, which is mass times gravity, so 15 kg times 10 meters per second squared. Multiplying that by 1.5 meters gives us 225 Newton meters, or joules. This shows us how much work the porter does just to lift the luggage. Now remember, if the force and the displacement are in opposite directions, the work is negative. And if the force is perpendicular to the displacement, like holding a bag out to the side without moving it, that work is 0. And as a quick reminder, the acceleration due to gravity we're using here is 10 meters per second squared. Understanding these concepts helps us see how work relates to force and motion, which is fundamental in analyzing physical situations and overall energy transfer. Now, let's talk about energy. Energy is essentially an object's capacity for doing work. Think of it as the ability to make things happen. The unit we use to measure energy is the same as for work, which is the joule, abbreviated as J to put that into perspective. 1 joule is the amount of energy needed to do 1 joule of work. And if we need larger quantities, we just use kilojoules, where 1,000 joules equal 1 kilojoule. Energy comes in many different forms. There's heat energy, which is what we feel as warmth. Light energy, like the energy from the sun or a bulb. Chemical energy, stored in things like batteries or food. Mechanical energy, which includes both potential energy, the energy stored due to position, and kinetic energy, which is the energy of motion. And lastly, electrical energy, which powers most of our devices. Understanding these different forms helps us see how energy is all around us, powering everything from our daily activities to complex systems. It's a fundamental concept that connects directly to how we use and transfer energy in various processes. Let's talk about kinetic energy. This is the energy an object has because of its motion. Any moving object, whether it's a falling coconut, a speeding car, a flying aircraft, flowing water, blowing wind, or even a running athlete, all possess kinetic energy. It's a fundamental concept because it helps us understand how energy is transferred and transformed in various situations. Now, a key point to remember is that the kinetic energy of an object depends on its speed. The faster an object moves, the more kinetic energy it has. Think about it. A slow-moving bicycle has less kinetic energy than a fast-moving motorcycle. This relationship is crucial because it shows how energy increases with velocity. This brings us to the formula for kinetic energy. The energy, which we denote as E, depends on the mass of the object, m, and its velocity. V. The formula is E equals 1/2 times m times v squared. In symbols, that's E equals 1/2 mv squared. Notice how velocity is squared. That means doubling the speed actually quadruples the kinetic energy. Let's consider an example to make this clearer. Suppose we have an object with a mass of 15 kilograms moving at 4 meters per second. Using our formula, we multiply 1/2 by 15 and then by the square of 4. That's 4 squared, which is 16. So the calculation becomes 1/2 times 15 times 16. When you do the math, you get a kinetic energy of 120 joules. This example highlights how the formula helps us quantify the energy an object has due to its motion. Understanding this concept is essential because it links the physical characteristics of objects, their mass and speed, to the energy they carry. This understanding forms a core part of analyzing energy transfer in our overall study of physics. Potential energy is all about the energy an object has because of its position or shape. Think about a stretched rubber band. When you let go, it snaps back to its original shape. That stored energy when stretched is what we call potential energy. Similarly, when we wind up a toy car, the spring inside gets energized. Once released, that energy transforms into motion, making the car move. It's a great example of how energy can be stored and then used to do work. And of course, lifting an object to a height is another classic example. When we lift it, we're transferring energy to it, storing it as potential energy. When we let go, gravity takes over and the object falls, converting that stored energy into movement. All these examples show how potential energy depends on position or shape, and how it plays a key role in the way energy is transferred and transformed in everyday situations. This concept helps us understand the foundation of energy in motion and stillness. Now, let's talk about gravitational potential energy. When you lift an object to a certain height, its energy increases because work has been done on it against gravity. This stored energy is what we call gravitational potential energy. The key idea here is that the amount of energy an object gains depends on how high you lift it, and this relationship is captured in a simple formula. If an object with mass m is raised to a height h from the ground, the work done on it, which equals the energy gained, is calculated by multiplying the force applied, which is the weight of the object, by the distance it's moved upwards. So the work done is mg times h, or mgh. This is also the potential energy that the object now possesses after being lifted. To put this into perspective, let's do a quick example. Suppose we have an object that weighs 10 kilograms and we lift it 6 meters above the ground. Using gravity as 9.8 meters per second squared, we can calculate its potential energy. Plugging in the numbers, we get 10 times 9.8 times 6, which equals 588 joules. This example helps illustrate how the height and mass directly influence the energy stored, highlighting the importance of the relationship between gravity, mass, and height in potential energy calculations. Now, let's talk about the transformation of energy. This is all about how energy can change from one form to another. For example, when you turn on a lamp, electrical energy is transformed into light and heat energy. It's important to remember that during these conversions, the total amount of energy stays the same. This principle is known as the conservation of energy. No energy is lost or gained in the process. It just changes from one form to another. Understanding this concept helps us see how energy flows and transforms in everyday life, which is a key part of grasping the overall energy system we're exploring today. Let's talk about the law of conservation of energy. This fundamental principle states that energy can only change from one form into another. It cannot be created out of nothing or destroyed completely. What's really interesting is that the total amount of energy remains constant before and after any transformation. For example, imagine an object falling freely from a certain height. At the very beginning, it has a lot of potential energy because of its position. As it starts to fall, that potential energy gradually converts into kinetic energy, the energy of motion. So, as it falls, the potential energy decreases, but the kinetic energy increases correspondingly. By the time the object is just about to hit the ground, its kinetic energy is at its maximum, while its potential energy is at its minimum. However, if we add the two energies together, potential plus kinetic, they always sum up to the same total energy from the start to the end. This example really highlights the core idea. Energy is conserved, just changing forms along the way. It connects directly to the overall theme of energy transformations and helps us understand how energy flows in different systems. Now let's talk about the rate of doing work, which we call power. Power essentially measures how quickly work is being done. If we say that W is the work done in a time t, then the power is calculated as work divided by time. In other words, power equals work done divided by time taken, or simply, P equals W over T. The unit we use to measure power is the watt. Symbolized as W, 1 watt represents the power of an agent doing work at the rate of 1 joule per second. So, if someone or something is doing 1 joule of work every second, they are using power at a rate of 1 watt. To put it simply, 1 watt equals 1 joule per second, or in notation, 1 W equals 1 J divided by 1 second. We also use larger units for more powerful machines or systems. For example, 1 kilowatt equals 1,000 watts. That's 1,000 times more power than a single watt. And breaking it down further, 1 kilowatt is the same as 1,000 joules per second. This helps us understand how much work can be done per second at higher power levels. Connecting this to our overall theme, understanding power helps us grasp how efficiently and quickly work is being performed, which is crucial in designing and analyzing mechanical and electrical systems. Now let's discuss the commercial unit of power, which is the kilowatt hour, or kWh. This is the standard unit used to measure electrical energy, especially in homes and industries. A kilowatt hour represents the amount of energy used when a device consumes power at a rate of 1 kilowatt over the period of 1 hour. To put that into perspective, 1 kilowatt equals 1,000 joules per second, or 1,000 watts. So, if you use a 1,000 watt appliance for 1 hour, you've used 1 kilowatt hour of energy. Mathematically, this is calculated as 1 kilowatt times 1 hour, which equals 1,000 watts times 3,600 seconds, since 1 hour has 3,600 seconds. When you do the math, that amounts to 3.6 million joules, or 3.6 times 10 to the power of 6 joules. This conversion is important because it helps us understand just how much energy we're consuming in everyday life. In practical terms, the energy used in homes and industries is expressed in kilowatt hours. For example, the electricity bill often shows the consumption in units, where 1 unit is equal to 1 kilowatt hour. So, whenever you see your electricity meter reading in units, it's simply indicating how many kilowatt hours of energy you've used over a certain period. This connection between the unit and actual energy helps us better understand our energy consumption and manage it efficiently.